Hey everybody, how's it going? Now we are in Chapter 6. So, Chapter 6, we are going to be taking a look at random variables. So, the objectives of this chapter, let me see if I can straighten this out a little better. There we go. The objectives of this chapter distinguish between discrete and continuous random variables. We're going to determine the probability distribution for a discrete random variable. We will describe the connection between probability distributions and populations, construct a probability histogram for a discrete random variable, and then compute the mean of a discrete random variable, compute the variance and standard deviation of a discrete random variable. So lots to do. This is a longer section, so let's get started. All right, distinguishing between discrete and continuous random variables. If we roll a fair die, the possible outcomes are the numbers 1, 2, 3, 4, 5, and 6. So each of the numbers has a probability of 1/6. We already know that. We've learned it before. Rolling a die is a probability experiment whose outcomes are numbers. The outcome of such an experiment is called random variable. So a random variable is a numerical outcome, has to be a number, of a probability experiment. So discrete and continuous. The discrete random variables are random variables whose possible values can be listed. Examples will include the number that comes up on the roll of a die, the number of siblings a randomly chosen person has. So those you can count, you can list. You're not going to have 1.5 siblings, and you're not going to have a decimal or a fraction when you're rolling a die. Now, continuous random variables include maybe the height of a randomly chosen college student. And the reason is height is continuous variable because maybe they say they're 6 foot, maybe they say they're 6'1", maybe they say they're 6'1 1/4". Maybe there's 6.17358. So there's really no limit to the numbers between any intervals. And when there is no limit to numbers between intervals, then it becomes a continuous random variable. The amount of electricity used to light a classroom is also a random variable, once again, because you have decimals and fractions that could go on for a long period of time. And there's an infinite number of decimals and fractions in between the whole numbers. All right, so let's determine a probability distribution for a discrete random variable. Probability distribution for a discrete random variable specifies the probability for each possible value of the random variable. So keep in mind again, probability has to be between and equal to 0 and 1. The sum of the probabilities of a probability distribution always will add up to be 1. Excuse me. So if I take a look at this one, as soon as I see this and I have a negative probability listed, that's a problem because we don't have negative probabilities. Excuse me. This one, let's see, here are my outcomes. Outcomes could be positive or negative, so that's okay. So let's add up our probabilities and see if they have a sum of 1. When I add them together, I do get 1. So this is a good probability model. All the probabilities are between 0 and 1, and they all add up to 1. So that's the key things you want to see. Are these all between 0 and 1, and does this column add up to be 1? Right away, when I see this 1.02, I know this cannot be a correct probability model because it has a probability on there that is bigger than 1. So it can't have a probability that's bigger than 1, and certainly it's not going to add up to 1 if one of the probabilities is bigger than 1. All right, let's look at computing probabilities. 4 patients have made appointments to have their blood pressures checked at a clinic. X is going to be the number of them that have high blood pressure. The probability distribution is as follows. Okay, so the first thing it says is we're going to find the probability of 2 or 3. Now, the events 2 and 3 are mutually exclusive events since they can't both happen. You can't both have 2 and 3 people having high blood pressure. So we're going to use the addition rule that we learned back in Chapter 5, probability of 2 plus the probability of 3, and we find out that the probability is 0.35. 4 patients made appointments to have their blood pressures checked again. Let's see what the probability is that more than one person will have high blood pressure. Well, more than one person means that they're going to have 2, 3, or 4. So you would add your 2, 3, or 4 together, and then you can get your 0.36 for your probability. What about at least 1? So at least 1 means 1, 2, 3, 4. Now you could add all these together, or you could take the 0 that's not included and take the complement. So if we use the complement rule, we can say what's the probability of at least 1? That would be 1 minus the probability of getting 0. So you would have 70.77 as your probability. Objective 3, describe the connection between probability distributions and populations. Now remember, population just means everything that you're talking about. So populations aren't necessarily huge. They could be small as well, because if that's all the possibilities there are, then that's the population. So statisticians are interested in studying samples drawn from populations. Random variables are important because an item is drawn from a population. The value observed is the value of the random variable. The probability distribution of the random variable tells how frequently we can expect each of the possible values of the random variable to turn up in the sample. So we have an example here. We have the airport parking facility that contains 1,000 parking spaces. Of these, 142 are covered long-term spaces that cost $2 an hour. 378 are short-term spaces that are covered that cost $4.50 an hour. 423 are uncovered long-term spaces that cost $1.50 an hour. 57 are uncovered short-term spaces that cost $4 an hour. Parking spaces selected at random. Let big X represent the hourly parking fee for the random sample space. So find the probability distribution of X. So let's take a look. Now, the probability distribution, we have to list the values of X and find the probabilities of each one of those. So we know we have 150, 2, 4, and 450. So let's look at those probabilities. So the spaces costing 150 are 423 parking places over 1,000. Costing $2 is 142 over 1,000. Costing $4 is 57 over 1,000. And then finally, the number of spaces costing $4.50 would be 378 over 1,000. So these are your probabilities for each of your total outcomes. Now, when you line up, this is the amount it costs per hour with the probability. And again, a double check is always adding these together to make sure that they add up to be 1. If they don't, then you did something wrong. I always like double checks that let me know if I did something wrong. All right, so when we draw a sample, we compute a sample mean. And a quantity, X mean, is random variable because its value is different for different samples. So obviously, if you pick one sample, you'll get one mean. If you pick a different sample, you'll get another one. So the probability distribution for X bar is usually difficult to compute. We will learn how to approximate the probability distribution of the sample mean when the sample size is large in a later chapter. I'm not sure if we're going to get to that section or not. We will see. Objective 4. Constructing a probability histogram for a discrete random variable. Okay, so here's the probability distribution that we have. This following represents the number of boys in a family of 5 children. Using the assumption that boys and girls are equally likely and births are independent events, this is your probability model. And notice it is a normal curve. Okay? So, again, you want to make sure that this adds up to be 1. Here are your probabilities along your vertical axis. Here are your results that you're looking at, 1, 0, 1, 2, 3, 4, or 5. And there's your probability model for your histogram. All right, compute the mean of a discrete random variable. Now, the mean is a measure of center, remember. The mean of a random variable provides the measure of center for the probability distribution of a random variable. So to find the mean of the discrete random variable, we're going to multiply each possible value by its probability and then add the product. So notice before, we would just take the sum. Now we're taking the sum of what it is times its probability. So here I have computer monitors where it has defective pixels. It might have 1, 2, or 3 defective pixels. That X represent the number of defective pixels in the monitor. The probability distribution of X is as follows. So let's find the mean. So what we would have to do is take each one of those possibilities. Of course, we're going to have 0 times 0.2. How did I get that? Well, if I add up my probabilities, then I'm going to see that I still have 0.2. And I have 1 times 0.05, 2 times 0.02, 3 times 0.01, and I get the mean of 1.2. So, if we imagine a rectangle, again, if you remember, the mean is the balance point of your model that you have. Okay, there are occasions in which people want you to predict how much they are likely to gain or lose making a certain decision. Often this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value. If the expected value is positive, it is an expected gain. If it is negative, it is an expected loss. Now, you'll see this a lot of times when you're looking at casinos and gambling and how they're figuring out what those values would be. And, well, let me just tell you, the house always wins. So, here we go. Let's take a look at this. Here we have a mineral economist estimated that a particular venture had a probability of 0.4 of a $30 million loss and a 0.5 of a $20 million profit and a probability of 0.1 of a $40 million profit. So we're going to let X represent the profit and find the probability distribution of the profit and expected value. Does this venture have an expected gain or an expected loss? Let's take a look. Oh, that's not good. Let me close that out there. Hopefully it'll be long enough to keep us through this section. Okay, I just looked at something in the book. Let me back up a minute. Hopefully you notice this is not the right probability model in this corner. I just saw this in the book as I was going through the page. I'm like, wait a minute, this isn't correct. You can't have a probability of negative 0.1. So this isn't correct. So the correct probability table in here is on page 259. You take a look at that, and that's where it'll show 0 at 0.2, 1 at 0.5, 2 at 0.2, 3 at 0.1. It's 1.2. So Looks like I'm going to have to screen these a little bit better before I put them up. And this is not correct. All right, now let's go back to where we were. All right, let's see if we're going to have an expected gain or an expected loss. Is it going to be worth it? Okay, the probability distribution is as follows. If 30 is negative, it represents the loss. Again, this should add up to be 1. And I'm going to take my values, negative 30 times my probability of it, my 20 million times my probability of it, my 40 million times my probability of it, and I will get 2 million. So there's an expected gain of $2 million. So what this means is you might have, it says a mineralist, so maybe this is a coal company and they're looking at these projects and maybe there's several of them. So if you're going to have a probability of these values, that means sometimes you win, sometimes you lose. Is it going to be worth it in the end? So I'm not sure if they would think it would be worth it for just 2 million when you have all these large numbers. So that they would have to determine that after getting this information. All right, computing the variance and the standard deviation of the discrete random variable. If you remember before, the variance was the value, subtract the mean, and then square it. Notice the only difference that we have here for a discrete random variable is we still have that value, subtracted the mean, and we're still squaring it. This is all the same from before. Now you multiply that by the probability. Now they also say this is another way that you can do it here. You can either take your x squared times your probability and then subtract your mean squared. Find the sum of those. They say that can be easier when you're doing it by hand. So the standard deviation is just like the standard deviation that we looked at before. As long as you have your variance, then you're going to take your square root of your variance, and then that will give you your standard deviation. So nothing has changed there. So it's very similar to what we did before, but now that we're looking at probability distributions, you have to add that value in there as well. All right, so they also give you how to do it on your TI-84. Again, we're going to use our list and enter the variables in there. We'll go over to calc. We'll hit one variable statistics. Oh, let's see. Oh, here we go. Here's an example. I'm going to put these values in, L1, these values in for L2. We run the one variable statistics, L1, L2 command. And here will give you the values that you're looking for. So here's your 1.2. Now notice it says X bar. And notice over here we have mu. Why? Well, we put in the entire population. The calculator doesn't know necessarily that it's the entire population. So since we have a list, it's just giving us X bar. So that's okay. It's not a big deal. All right, and then here's our standard deviation as well. All right, so that was a lot. The difference between discrete and continuous, how to determine the probability distribution for discrete random variable, how to construct a probability distribution for a population, how to construct a probability histogram, and how to compute the mean, variance, and standard deviation of a discrete random variable. So hopefully that was all good for you. And as I've been saying, I know you're getting a lot of information thrown at you. So it's going to be very important that you organize yourself and that you have some kind of system to look back and make sure you know what formulas you need to use for what situation. Alrighty, so I will see you for section 6-2.